introduce Franco Flandoli, Professor Franco Flandoli from the University of Pisa, and he will speak about uniqueness due to noise for a dyadic model of turbulence.
Thank you very much. Thank you to all the organizers, especially to Giswa for his support for everything, make everything easy. I will talk about a simple model. It's a system of infinitely many differential equations coupled together. The model has this shape. So you have to think that xn is a function of time, real valued, and this is a system for n greater or equal than 1, an infinite system. They are coupled only in the nearest neighbor in this very special way. The numbers, the coefficient kn, I will take of the form lambda to the power n with lambda greater than 1, but one can do something more general. There is an initial condition that I denote this way, and this is studied for t greater or equal than 0. The first equation for n equal 1 is coupled with 0, so I have to impose that x0 of t is identically 0, and also sometimes it's useful to have this. So essentially, apart from details, there is kn goes to infinity very fast, and this system is coupled in this way. It has a name in the literature. It's called the dyadic model of turbulence. It was developed by a group, I will list, maybe I just say the names, Katz, Pavlovich, Cheskidov, Freelander, some beautiful paper also of Kisielev, Zlatlos, and also other people work on that. I will describe a series of results on this problem, sometimes plus noise, with and without noise, a series of results that we got with my collaborators Barbato, myself, and Morandin. I will shorten BFM, a series of papers that are very recent. So let me start, this is more or less the equation. Let me start with some heuristics to understand what we can believe. First, maybe the following remark, that why people study this system, because has something in common with typical equations of fluid dynamics. My viewpoint is Euler equation, three-dimensional Euler equation, but other people think Burger's equation for other reasons. So there are similarities with three-dimensional Euler equation. Let me remember, even if I don't use it, let me write Euler equation as this kind of equation with divergence 0. The similarities are simply that quadratic nonlinearity, infinite dimensionality, and mainly formally energy preservation. Formally constant energy.
Is it Hamiltonian, Franco?
Could you repeat?
It's Hamiltonian. He's asking. Hamiltonian system.
Okay. I think so, but I didn't check. So it's a formally constant energy. I didn't try to write in like Hamiltonian system. Differences are that, of course, if you write Euler equation in Fourier modes, the coupling is there is an infinite coupling of Fourier modes. Another difference that there are no squares in the Fourier description of Euler equation. So, among the similarities, there are also the results. There are results which are similar to Euler in some sense, and others which are more than Euler because it's easier to understand this instead of Euler. Let me describe some heuristic about this equation. Let me introduce the energy. The energy is the sum of xnt squared over all components. And also, let me write the sum up to, if I stop to n, I write En. So also n finite or infinite. And you have to think that if you take the first n point, you have to think that there is a profile which is the value of x1, x2, and so on, somewhere the value of xn. And the energy, I'm talking about the energy of this block. This is En. And then the system continues. And I would like to understand what happens to the energy in time. Very simply, the computation is these are simple remarks just to start to have an idea. If we differentiate xn square, we get kn plus n minus 1 square xn minus kn xn square xn plus 1. So you see that this is as a telescopic nature. So when we introduce En, we sum over the first component. So the time derivative, they cancel each other, and the only terms which remains is kn xn square xn plus 1. So formally speaking, the time derivative of the full energy is 0. Rigorously speaking, this would require some kind of summability of the coefficient. So in this sense, I say that is energy preserving like Euler equation. I underline formally because this result will be shown to be not true. And the other fact that we see from this simple formula is that we can play with positivity or negativity of coefficients instead, something that we cannot do for Euler. In particular, this coefficient kn are always positive in our choice. This is a square, so everything depends only on one component. So for instance, we have that if xn plus 1 is positive, then the corresponding energy decreases. So the energy of a block decreases when the value here is positive. If here there is a positive value, this energy flows on the right. And we can say the following. Assume, for instance, that xn behaves like kn to the power 1/3. Then under this scaling plus positivity, so let's say also positivity, we see that the derivative of an is roughly constant. And if the derivative of the energy is more or less constant for every level n, the intuition is that energy flows in this direction infinitely fast. So there is a dissipation of energy. Dissipation of energy. Dissipation in the form of a dispersion to the right of the energy in finite time. And this will be strictly true as a result under some condition. Another remark is that you see, positivity implies that the energy goes down. Negativity of a component implies that so this is a sort of direct cascade. And otherwise, if a coefficient is negative, there is a sort of inverse cascade. Positivity is robust. So positivity is robust. Is a robust property. If an initial condition for one component, I'm not assuming for all components, if one component at some time, at the initial time, is positive, then the solution is positive forever. This can be seen right in, I shorten a little bit due to time, so I don't write the proof. You see, it's sufficient to write the variation of constant formula using this xn here, and consider this like a forcing term, which is positive, and so you immediately see that a positive initial condition plus this positive forcing produces a conservation of positivity for each component. And so this phenomena of a flow of energy to the right is a robust phenomenon.
The solution for all time?
Sorry?
You have solution for all time?
Now I give some definition and theorems. This is more or less the heuristic I wanted to describe. First a definition. Okay, so first a definition. This definition is obvious. What I mean by solution, a solution is an L-infinity function of time with values in small L2. I want the energy finite. A solution on a finite time interval otherwise. And I require that the components are continuous. The components are continuous, and the equation is satisfied, plus the equation. So this is the definition of solution. If I say le re, I require that the energy at time t is smaller than the energy at time 0 for every t. Le re, I mean this one. And first remark is a theorem, but with a very easy proof. Theorem, there exists le re solution for every initial condition in L2. I denote by x, I denote by small x the sequence xn, and capital X the sequence xn.
Unique form, right?
Sorry?
But not unique.
This is the main topic of the talk. The uniqueness is the main topic. So this is an easy theorem by Ascoli Arzellasam. Very, very easy reason. Let me come to main theorems. Main theorems. Maybe four, I don't remember. Main theorem. Theorem 1 is proved in a paper on transaction. Theorem 1 says that if we take initial conditions in small L2 with positive components for every n, then the energy decreases to 0. The energy decreases to 0. We have an estimate which is decreases like 1 over t squared.
Say,
But,
for example,
in a-
the
in a
energy
week.
of some solution, that energy of some solution decreases to zero.
All solutions.
Of all solutions.
All solutions. Sorry. Yes, there will be. Okay. I don't want to anticipate theorem 3 or 4, but under this condition, the solution is unique. Under this special condition of positivity. Anyway, for all solutions, the energy goes to zero before we know the uniqueness. The proof of this is not easy, is intricate, and not very direct, let's say. Okay, are estimates of the energy of a block of n with respect to the energy of block n minus 1 with some tricky computation. Apart from the proof, we tried to see what happens numerically, even if we cannot prove what we see. And numerically, the picture is the following one. The picture is assume, so this is 1, 2, and so on, like this drawing here. So I think to the profile X, start with a positive profile like this, for instance. Next step, next numerical step is that it builds a shape like this one, which is nail with a head. I cannot prove this head, but it's very important. And the snail becomes a turbo snail, because when this shape appears, this starts to go on the right very fast with acceleration. And in finite time, this shape becomes infinite. So in finite time, we see this. And this behavior is exactly kn to the 1/3, the one which comes immediately from trivial computations. And when this is built, this shape is built, then it starts to go down, to dissipate. This is not dissipation. This is just a distribution of energy on the right, and then this starts to go down in a self-similar way. What we have proved in the same paper is that there exist self-similar solutions. Solutions of the form xn of t equal an over t. They go down like t, the energy goes down like t squared, and an is asymptotically kn to 1/3. There exists a similar solution. The proof of this theorem is really very difficult. So we don't have a proof of these steps, let's say, of some genericity of these steps. If we start with negative shapes, okay, no, this is another story. But we have a proof at least of the last bit of story. So this is for dissipation. Dissipation has immediately a consequence, which is non-uniqueness. Non-uniqueness for some special initial condition. So theorem 3 or corollary is there exist initial conditions in L2 with all negative components such that no uniqueness. Let me explain how to build them. This drawing is in time and energy. Time and energy. Start with an initial energy E0. The solution, the components are negative, but the energy, of course, is positive. Start with initial energy A0 from an initial condition which is like these ones, which is like what we construct by a dissipating solution. Reverse the dissipating solution, because the equation is invariant by inversion of time. And so build a solution with increasing energy. So this by time reversion. Time reversion of theorem 2. no, of theorem 1, let's say, either 1 or 2. One can reverse the self-similar or any dissipating solution. And everywhere, like here, you can start with a Leray solution, which can be constant or decreasing. There is always a Leray solution from any configuration. So, so this increasing energy solution branches everywhere. And so we have this non-uniqueness. I forgot to say until now what is common with the Euler equation. For there are papers of Schnirelman, Scheffer before, and recently Camillo De Lellis and Laszlo Zegelidis. Let me shrink. Let's say altogether, essentially, they prove the existence of solutions which dissipate energy for Euler, and the existence of initial condition with non-uniqueness. Depends on the paper. So these results are common to Euler equation. Not common to Euler equation is the existence of solution. The trivial theorem above of existence of Leray solution is not known for Euler equations, for instance.
Excuse me, can you make this solution smooth with fast decay? With fast decay makes sense?
Yes. If there is the beautiful paper of Kiziev and Zlatos, they prove the following. If you start with an initial condition of class H1, you can believe which is the definition of H1 here, the solution loses H1 regularity in finite time. All H1 solution become less than H1 in finite time. So infinitely regular solutions don't exist, let's say. There is singularities in finite time for all initial conditions. This is also a result, let's say, unproved for Euler equation. I mean, it's an open problem, famous open problem for Euler equation, the existence of singularities. So this is also, I should mention this result because this is a reason to work in small L2. I mean, we have to work in small L2 or maybe some intermediate space between small L2 and H1 because certainly H1 is too much for global solutions. Okay. And let me stress here that this non-unique, the only examples we have on non-uniqueness, maybe there are others, but the only examples we have of non-uniqueness are built on the following following mechanism, which is similar to the proof of Schnirelman dissipation, on Schnirelman non-uniqueness. Energy which comes from plus infinity, because we reverse time to solution which dissipates energy this way. So this solution with increasing energy, they pump energy from minus infinity. This is the only mechanism that we have discovered, but maybe there are others. Let me mention the uniqueness we know for the deterministic, and then I pass to the stochastic. For the deterministic, for this deterministic model, the only uniqueness, apart from local uniqueness for regular solution, but the only uniqueness result we know is the following one for positive solution under the same assumptions of theorem 1, I believe. Positive solutions. So I lost a little bit. Theorem 4 is theorem 4. This is in a paper on Grass, again 2010. The other were on the paper on transactions. If X is L2 with all positive components, then we have uniqueness. Uniqueness of solution in those sense. Automatically they are Leray solutions. So, okay, I'm not giving any proof because it depends on time, and maybe I will give some sketch at the end, depending on time. So, the picture, I would like to explain the picture that emerges. Now, think that in the space small L2, we have, by theorem 4, we have a thin set, because unfortunately this is a small set, of initial condition for which we have uniqueness. And we have an extra thin set of initial conditions where we can build this kind of counterexamples. If we believe in these numerics, this set is really very, very small. It's presumably extremely small perturbations of this self-similar shape. So this, from this set we have non-uniqueness. So the question concerning uniqueness now is how much is generic, the one phenomena or the other, which is the what is generic? What is generic? If we believe, but we have no proof that the only mechanism of non-uniqueness is pumping energy from plus infinity, this may happen only when, let me write it, only when, let's say, all components are negative. Let me write more precisely. I can probably write it here. The energy may increase only if the components are negative for all n greater than some n0. If definitely all the components are negative, then energy may increase, otherwise not. So if we believe that the only way to have non-uniqueness is by this mechanism of increasing energy, then the set of pathological initial condition is small, because the set of points with all negative components or most negative components is small. So this is presumably small. Presumably small. About uniqueness, we don't know. This theorem in class of uniqueness is more general. What I wrote is a corollary. We have a more general criteria, but this criteria is not very easy to understand how many initial conditions it takes. So and now comes the stochastic. It has many motivations, the stochastic. One is about this understanding. If the non-uniqueness comes from pumping energy from infinity, and this can be done only with negative components, if we introduce noise and the noise changes just a little bit the sign of components in a random way, that it produces barriers to the injection of energy from minus infinity. So assume that the noise changes infinitely many, not all, infinitely many of these components, the sign, then these infinitely many components are a barrier so that energy cannot enter. This is just intuition. The theorem says this, but in a more abstract way. So let me express the theorem. This theorem can be found in a paper on Proceedings, American Mathematical Society, 2010. The theorem says the following, that with noise, the noise, I want to describe the noise with care, with suitable noise, for every initial condition, we have uniqueness. There exists a unique weak solution. Weak also in the probabilistic sense. Let me give details of the kind of noise, the definition of solution, and something else. So first, the kind of noise we introduce. the idea of introducing the following noise comes from PDEs. Consider again Euler equation. There are papers, maybe not strictly on Euler equation, but on similar models like Navier-Stokes or diffusion of passive scalars. There are papers where the noise is the gradient of U times noise. Times noise, let me write dW in dt. This is a space-time noise. And Stratonovich. For instance, Mikulevicius yesterday essentially considered a model like this because there was an Ito noise, but there was the Ito correction with the Laplacian. And also diffusion of passive scalar. This is the typical noise that is considered. If we, in an imaginary way, because there is no relation between Euler equation and that equation, imaginary way, we translate this kind of noise at that level, the equation must be of the form the same deterministic part plus we have to replace, for instance, this term. We have to replace one of the x by noise, and essentially nothing else. So what I choose is k n minus 1 x n minus 1 Stratonovich d w n minus 1 minus k n. This is more tricky. This is a little bit more tricky. K n x n plus 1 Stratonovich dwn. Let me immediately show that this, where, of course, Wn is a sequence of independent Brownian motions, real-valued Brownian motions. Let me show immediately that this special choice, we can put a coefficient sigma in front here, but not so many other modifications. Let me show that this choice preserves energy at the formal level. Again, you know that Stratonovich calculus is like deterministic calculus, so I will act like Wn are smooth functions at the formal level. So the derivative of xn square is equal to the part from the deterministic one, as before. And here we have, let me drop sigma, which just complicates notation. Kn minus 1, xn minus 1, xn dwn minus 1, kn xn xn plus 1 dwn. So again, it's telescopic. It's a telescopic series, you see. And so, if we sum, formally speaking, the derivative of the energy, formally speaking, is 0. This is the equation. The definition of solution is rather natural. Is easier to give the definition rewriting the system in Ito form. So let me write the Ito form. Ito form is dxn equal the deterministic part plus the same stochastic part in Ito. I write it for completeness. And then the correction, which has this shape. Let me drop the computation. I hope that my memory is correct. This is the correction, which is like a Laplacian, like in the equation for passive scalars. If one rewrites in Ito form, there is a Laplacian, but it's a fake Laplacian because the equation is conservative. There is no regularization. So there is formally this. Anyway, now it's Ito, so it's easier to give the definition of solution. I want a weak solution in the probabilistic sense because I can prove only that. So I say that the concept of weak solution is a probability space, a filtration, a filtered probability space, a sequence of Brownian motions, a sequence of processes with the proper. I ask that X is L infinity with values in small L2, and the components are continuous adapted. Xn are continuous and adapted, and then the equation is true for every n, plus the equation true for every n. So now with this definition, the statement is clear. We can prove weak existence and weak uniqueness for every initial condition. I can try to give an idea of proof of this result, which mainly the reason I give the proof is that is really, in a sense, a non-standard proof. It's nothing traditional with respect to usual proofs I know. I learned this, the idea of this proof from Professor Magliaven, but his description was in geometry in infinite dimensions, so is apparently maybe disjoint from what I will do, but I'm sure that I learned from him this proof.
Why is that called a weak solution? You say it satisfies the equation.
Sorry?
Why do you call it a weak solution?
Because I don't prescribe a priori this the first part of this object. Okay. Or you can say in other way, say just don't ask that X is adapted to W, let's say, but X is adapted to the filtration. But sorry, when I say adapted, yes, sorry, to the adapted to the filtration, not to the noise. Sorry. Adapted to the filtration. Let me show a sketch of proof. The first there are 3 steps. The first ingredient is Girsanov, which looks classical, but we have to use a very strange Girsanov. Maybe somebody will tell me that there exists already a paper with this kind of Girsanov, I don't know, which is, unfortunately, I shortened a little bit because I wrote dots. But if I allow me to expand these dots, you will see that, and unfortunately I canceled the deterministic part there, but you can see that there is, let me rewrite, there is kn minus 1. From here there was xn minus 1 square, and I split it in xn minus 1, which multiplies xn minus 1 plus dt plus dwn minus 1. And the other term was kn, there was xn plus 1, xn plus 1, I put xn plus 1. Here the other term contained xn plus 1, so I put xn plus 1 here, and it remains xn dt plus Stratonovich dwn. So you see the structure. I change, I call this Stratonovich dbn. So I introduce the following objects. Bn of t are wn of t plus the integral of xn s ds. and these are Q Brownian motions. Is a sequence of independent Q Brownian motions with respect to a Q, which is given by dq over dp. P is the original probability. dq over dp equal to exponential of restricted to the filtration ft or small t. This is integral, then x of s scalar dws in small l2 minus 1/2 integral of x of s square in small l2 in the s. Fortunately, I can handle this equation is compatible with this kind of condition, so it's very easy to have a Novikov condition in order that everything here is correct, is rigorous. So by Girsanov, we reduce to the equation dxn equal, I just rewrite this equation by a new name, is a linear equation k n minus 1 x n minus 1 Stratonovich db n minus 1 minus kn x n plus 1 Stratonovich bn. So first step 1, reduction to linear equation. This is step 1. Step 2, which is not trivial, even if it is a linear equation, is okay. Sorry, I could use both of them. Step 2 is let me write the same computation as here, but for the linear linear. I was tempted to call it a linear transport equation because there is a strong inspiration from a parallel research that Enrico Priola will describe tomorrow on linear transport equation. This is a sort of linear transport equation. Let me do dxn square. Sorry, in Ito form, this is the same. Drop just this db. The same. Drop Stratonovich. Okay, let me drop Stratonovich and add the correction. The correction is minus k n minus 1 square plus k n square x n dt. This is the correction, the same correction that appeared in the other case. Girsanov is not sensitive of the kind of integration. Dxn square produces k n minus 1 produces when you apply the squares, there is a part with Brownian motion, which is a martingale. So let me shorten into dmn, a martingale part. Then there is this term multiplied by xn. So there is minus k square n minus 1 k n square xn square dt. And then there is the Ito correction. The Ito correction is a little bit tricky. We have to compute the bracket between the Ito correction is simply k n minus 1 square x n minus 1 square. There is 1/2. Also here there was 1/2 that I forgot everywhere. So there is a 1/2 here because this is the correction of Stratonovich. There is 1/2 here, x n minus 1 square plus 1/2 k n square x n plus 1 square in dt. The essential point of, so this is the Ito correction. The essential point of this identity is that taking expected values, there are only the expected values of the squares. A priori, if one makes the squares, there should be cross products, and they would break our argument. So let me introduce un of t, the expected value of xn square of t. It satisfies the time derivative dun in dt is equal to minus kn minus 1 kn square un plus kn minus 1 square un minus 1 plus kn square un plus 1. And it is also interesting to rewrite this, putting together the kn minus 1 square with minus kn times un minus 1 plus kn square un plus 1 minus un. So we see that is again a telescopic series. This is step 2. This computation is step 2, which is, I mean, the computation is easy. The result is remarkable. The fact that the squares satisfy a closed equation is very remarkable. And step 3 is uniqueness for this equation in the following sense. We want to prove, so let me, to understand what I'm going to do in step 3, let me summarize the logic line of the proof. The logic line of the proof is we transform the nonlinear to linear by Girsanov. Now, for the linear transport, we can prove strong existence and strong uniqueness. Unfortunately, it's Girsanov that produces weak. So for this, we can prove strong uniqueness. Existence, I don't show it. We can prove strong uniqueness. So take two solutions on the same probability space, take the difference, and prove that the difference is 0. Since it's linear, it's sufficient to take a 0 initial condition and prove that the solution is 0. So step 3 is assume that the initial condition is 0 and prove that the solution x is 0. The solution x of this linear problem is 0. So it is sufficient to prove that un of t is equal to 0 for every n and t. For every n and t. If the squares are 0, then with easy argument there is a continuity of components. Everything is 0. So I want to prove that the solution of this system, deterministic system, is 0, starting from initial condition un at time 0 is 0, because un at time 0 is just the initial condition, the n component of the initial condition squared. So I have a linear deterministic system with 0 initial condition, and I want to prove that the solution is 0. This is only apparently trivial. I mean, what is formally, if we take the sum of un of t and we differentiate, we can take advantage of the telescopic nature of this equation to show that this is 0. So if it is, and sorry, I forgot to underline that these un are by definition positive. These un are positive by definition. So we have a linear equation. We handle a solution which we know to be positive, to be 0 at the beginning, and we know, again by definition, we know that the series of un is finite. the series of un of t is bounded by a constant, because the series of un is the series of xn, and by definition we handle solutions such that the energy is bounded. So we have all these conditions and we have to prove this. Formally this is true by telescopic, but it is like a transport equation in which to make a computation rigorous is not trivial. At the end there is a simple proof, which is the following one. Namely, we avoid ideas like commutator lemma or so on, which could be another way to prove. I do the proof in the following way. Un, let me rewrite this equation in this form, in integral form. This plus integral of this plus k n minus 1 integral of un minus un minus 1 ds is equal, initial condition 0, is equal to kn integral of un plus 1 minus un ds. We know that, we know by assumption that this is positive, so we drop this, and this becomes an inequality in this sense. We know that u0 by definition is 0, u0 by definition is 0, u1 by definition is positive, so this term is positive for n equal 1. The coefficients are positive, so by induction all these terms are positive for every n. And then you see that we have, and then you see the end of the proof, because we have a sequence un with the property that the integral, for instance, the integral of un plus 1 ds is bigger than the integral of un ds, but at the same time the series converges, and so this implies that it must be 0. It must be 0, you see, this and this, it must be 0. And so this is the proof of uniqueness that you see is in some sense non-standard. It's not a usual estimate of differences. Sorry, I see the thing, so time is over. Thank you very much for your attention.
Questions or comments?
But this works only for sigma equal to 1, right?
No, for every sigma positive. This proof, I adopt sigma for simplicity of notation. You have a 1 over, you have 1 over sigma, 1 over sigma square. Until sigma is strictly positive, it works. So there is no difference.
This is a little bit surprising. When if I ever, I would expect the thing to go to the deterministic equation for sigma to 0, right?
For
So
sigma,
something I don't understand.
we have a working preparation which proved the following, that for the stochastic model, the unique solution dissipate energy for all initial conditions. And so in the limit when sigma goes to 0, we can prove that it selects a solution which dissipate energy.
The problem which I have is you are able to show for e of xn squared t that you have something which depends only on xn squared.
Yes.
As for the deterministic equation, I mean, if I look at it, that is not true.
There is a sigma which multiplies everything, because there is a sigma here and the sigma square here.
You want to? I was saying only. I mean, you were strongly using a kind of cancellation parts between the what appears in the Ito formula and the deterministic formula, right, to derive this closed form in terms of the UN.
Yes, simply cross products do not appear in Ito form. In when you do
But if I
that
just take,
computation, there are no cross products.
but what I'm saying, if you are not multiplying everything with sigma,
Oh, this is independent. So this is independent because the equation you can, apart that you can here you can absorb sigma inside the k. So you can just redefine kn like sigma times lambda to power n. So is the only point is that and here there is a sigma. So all the everywhere I need sigma positive also in this iteration. Otherwise, if this is 0, there is no iteration. No. Sigma here, after the sum of sigma multiplies all terms here with the square. So you can put sigma inside the coefficient. Probably it was fast and it's not clear, but our paper is written with sigma, and there is no mistake.
that's very. So I mean, in the end, you are saying, in the end, I get this equation. Now, what is the UN? With the
The
sigma.
definition of UN is the same. When there is a sigma, but here there is a sigma square here, and everywhere sigma square. And so, with the same definition of UN, there is a sigma square here. Everywhere there is multiplied by sigma square. Sigma can be absorbed in many ways also with a time change. So, I mean, it's not, as soon as it is strictly positive, it's not.
Maybe the thing that's confusing is that the expectation here is the expectation under the changed measure.
This is the expectation on the changed measure, yes. Yes. The argument, of course, is true for fixed sigma.
Change of measure.
If you want to send sigma to 0 is another kind of argument. For fixed sigma, the measure q depends on sigma, and everything is with respect to, at this level we have already changed measure, we leave in this, the new q.
But then it should still, I mean, there should be then, that's what I do not see, there should be a transformation if you look at it.
Just to postpone the discussion.
Yes.
Another question maybe in between. Just the noise you put in all components.
Yes.
Is it known if you put noise only in some, in few?
No, from this viewpoint, this
Why can't
result or the theory is quite rigid. We cannot change so much. It's quite rigid. We really have to. We have also a sort of abstract framework behind this with bilinear operators, namely the equation written in abstract form with bxx, and the noise must be of the form dwx. So the noise must be very precise. I don't exclude that one can do something in some direction, but at present our understanding is quite rigid. we need quite stiff.
No, it's
I
not
see that there are discussions still going on. But other questions?
Can you comment a little bit on the analogy between these two equations and the Euler equation?
finite blocks.
Because the results are quite remarkable, but
you mean the analogy for the deterministic problem or
already for the deterministic?
Already for the deterministic. The analogy is what I said is quadratic nonlinearity, infinite dimensionality. Some of the results are you find in both theories, like this existence of dissipation for some solution, non-uniqueness. But there is no most. I mean, there is a paper in the group of Freelander and so on that make a justification I mean, some Fourier analysis. But essentially, if you write Euler by Fourier, is too much more complicated. I mean, everything is different. It's only So of course we tried to extend what we did to we can reach finite range interactions, but for infinite range interactions we have to impose so many assumptions. I mean, Euler is excluded even in 2D from what we are able to do now at present.
Yeah, besides its complex coefficients.
And there is complex coefficients and so on. We would be satisfied to solve the GOI model at present, which is still a little bit not clear for us. I mean, so complex but finite range and so on. Very far away from Euler equation.
Other questions or comments? Doesn't seem to be the case. Thank you
Thank
very
you.
much.